Hello everyone. In this lecture, we will introduce the singularity continuous time signals. Now, what is the definition of a singularity signal? If this signal or its derivative has discontinuities, then this signal is a singularity signal. For example, for this SOT, it has discontinuities. At t equals to 1 and t equals to 2, there are two discontinuities. For this SOT, its derivative has discontinuities. Thus, these two signals are both singularity signals. The unit-step signal is one type of singularity signal. Here is the definition, and this is the waveform. It should be noted that U of 0 is not defined. The time-shifting version on this U of t is expressed in this equation, and here is a waveform. We can use the step signal to simulate switch circuit. For this circuit, when the switch is closed at t equals to 0, the current of the bulb can be simulated using U of t. And when the switch is closed at t equals to t sub 0, the current can be expressed using U of t minus t sub 0. The unit step signal can represent any rectangular signals. Here is one example. We can use the summation of two step signals to represent this SOT. Here is the expression formula. We can also use the step signal to represent any single-sided signals. For these two signals, the start point is 0. Thus, we can use U of t to represent the single-sided. For these two signals, the start point is t sub 0, and we can use U of t minus t sub 0. Some phenomena take effect instantaneously. For example, a bullet going through an apple or the lightning discharge. For this phenomenon, the duration of the signal is short, but the amplitude for this signal is large enough. We can use the impulse signal to represent this phenomena. Now, let's give the definition of the impulse signal. When t is not equal to 0, this signal is equal to 0, and the integration of the impulse signal is equal to 1. Here is a waveform. It should be noted that the 1 is the strength of the impulse signal. It is not the amplitude, and it is noted in the parentheses. Here is the time-shifting version for the impulse signal. For this signal, when t is not equal to t sub 0, the value is equal to 0, and the integration is equal to 1. Here, the integration interval may not always be minus infinity to infinity. If the integration interval includes this point, then this integration is equal to 1. Now, let's give the limiting form of other signals. Here is a rectangular form. The width of this signal is equal to delta, and the height is 1 over delta. Thus, the area for this signal is equal to 1. And here is a triangle form. The area of this signal is also equal to 1. When delta is approaching to 0, these two signals are impulse signal. Now, let's give the generalized form for the impulse signal. Here is the equation. In this equation, phi of t is a test function. It is an arbitrary continuous time signal. Now, how to understand this equation? If the integral of the product of the function with an arbitrary continuous time signal is equal to phi of 0, then this signal is a unit impulse signal. The unit impulse signal has some properties. The filtering property can be expressed in this equation. Here is a graphic representation. We can find that the resulting signal is also a dirt signal, but the strength is different. The sampling property can be expressed in this equation. Now let's give a proof. We first use the filtering property and we can get this equation. And then this part can move out of the integration and we get the result. Finally, for this integration, it is equal to 1, thus we can get the final result. The scaling property can be described in this equation. It can be proved with a generalized function definition. In this equation, when a is equal to -1, we can get dirt of t is equal to dirt of minus t. That is to say, the impulse signal is an even function. In this equation, we give the scaling property by adding the time shifting. Now let's give the relation between the unit impulse signal and the unit step signal. When we do differentiation on u of t, we get dirt of t. That is, for these discontinuities, the derivative can be represented using the dirt of t signal. And when we do integration on dirt of t, we can get u of t. Let's give a short description for this equation. When t is larger than 0, then this integration includes the point when t is equal to 0. Thus, the integration result is equal to 1. And when t is less than 0, then this integration interval do not include the point at t equal to 0. Thus, the integration result is equal to 0. In the previous slides, we know that the first derivative of a signal at the discontinuities is an impulse signal. And the strength for this impulse signal is a magnitude change. Let's give an example. For this SOT, its first derivative can be expressed in this figure. For these two discontinuity points, the first derivative is an impulse signal. For this one, the magnitude change is 2 minus 0, thus the strength is 2. For this point, the magnitude change is 0 minus 2, thus the strength is minus 2. Here is one example to evaluate the below equations. For the first equation, we can use the sampling property and we can get the result. For these two equations, the integration interval is not minus infinity to infinity. Thus, for this one, we should test if the integration interval includes t equals to 1, and this integration interval includes this point. Thus, we can get the final result. For this equation, the integration interval do not include the point when t is equal to minus 8. Thus, the final result is equal to 0. For these two equations, we should first use the scaling property. Using the scaling property, we can normalize this delta signal to this one, and then we can get the final result. For this equation, we also use the scaling property, and we can get the normalized expression. Now, the integration interval does not include the point when t is equal to 3, thus the final result is equal to 0. For the last equation, we can use the filtering property and the scaling property, and we get the final result. Now, let's give the usage of the impulse signal properties. When using the properties, we should pay attention to the interval of the integration. The interval integration may not always be -infinity to infinity. If the interval does not include t equals to t sub 0, then the integration result is equal to 0. When the impulse signals are in the form of this equation, we should first use the scaling property to normalize the dirt signal. The unit ramp signal can be expressed in this equation. Here is a graphic representation. Now let's give the relation between the unit ramp signal and the unit step signals. We can find that when we do integration on UOT, we can get ROT. And when we do differentiation on ROT, we can get the unit step signal. The unit ramp signal can be used to represent any triangle pulse signals. Here is one example. For this SOT, we can use the summation of these 3 ramp signals to represent it. And here is the expression formula. The doublet signal is defined in this equation. Here is a graphic representation. In this signal, it has 2 pulses. One is upward and the other is downward. The doublet signal has some properties, including the filtering property and the sampling property. The scaling property of the doublet signal can be expressed in this equation. When A is equal to -1 in this equation, we can get the following equation. That is to say, the doublet signal is an odd function. Based on this odd property, we can get the integration of the doublet signal is equal to 0. Now let's give a summary for this lecture. In this lecture, we introduce some singularity signals, including ROT, UOT, delta OT, and the doublet signal. This signal has the derivative relation, and they also has the integration relation. That's all. Thank you. See you next time.